Hello friends, welcome to Deep Learning Theory and Data Science. Uh, I'm going to cover some of the interesting slides from the previous and current semesters of Professor Vardan Papyan. Uh, I have picked some more advanced and more interesting slides from his course, and I'm going to present them here. Okay, I want to talk about information bottleneck here. Let's go and see what happens. Okay, as you can see, in information theory, we have a term called entropy, which is the minus sum of p of x times the log of p of x, and we sum iterate over different x's. The less entropy is, it means that, for example, if entropy is 0, it means that all of the information are the same. So we don't have any information, and the more entropy means we have more information. Okay. The conditional entropy is this term, is the usual entropy. We just changed it. We are conditioned on y, and so it is minus sum over the joint distribution of x and y, p of x and y log times log of p of x conditioned on y. Okay. Another thing that is very popular is Keil divergence, which is a Kullback-Leibler divergence, and it is asymmetric. It means that it's different. You put p, q, or qp here, and it is the sum of p of x log of p of x over q of x. Okay, so it's similar to entropy, but you are in the log you are dividing by q of x. Another thing is mutual information, which is symmetric. It means that there's no difference if you put x and y or y and x, and it is originated from the Keil divergence, the Keil divergence of joint of x and y and their their probability multiplication. And you can see if we put x and x here, it would become h of x minus h of x conditioned of h of x, and it would be 0. So if mutual information is 0, it means that the distributions are the same, and the more it is, it means that we have more if it is 0, it means that all the information are the same, and they're interpolate, or how can I say, yes, the shared area is the whole area between these two things, but yes, I think it's good. Okay. And another thing is invariance to invertible reparameterization. It means that there is no difference between mutual information of x and y and their reparameterization. Okay, so okay, you can see this is a network. This is x. It is y the true label. Is x the data, it is y hat the predicted label, and these are h1 to hm, which we call them x's, that are hidden layers. Okay, it's very important to note what is it. It is the mutual information between x and h, that h is the hidden layer, and it is the mutual information between x and y, between h and y. It means that each of these lines, I don't know, let me see if you see my okay, I think you see it. Yes, here. Oh no, what's that? Let me uh, delete this. Oh, how is it possible to delete this? Sorry, let me remove the things. Okay, here, each of these things are the uh, plus of one of the layers of this network, and yes, you can see that there are some lines. Let me zoom it in. As you can see, there are some lines from the right to left, and yes, it is an information plane. And uh, for example, we start from this bottom and we go to the up. I hope you see my mouse pointer. Okay, and here is the red line is the end of epoch. It is the 3999 epoch, and you see convergence here. Yes. Oh, another thing is that the mean or average of the gradients, how does it change? The mean value, decreases over time, but the standard deviation increases over time, because they are becoming this maybe the same, but they may become more noisy. You know what I'm talking about, as the epochs go. Oh, it's one of the most important inequalities that we have in data processing. It means that the mutual information between y and x is more than the mutual information between y and h1. H1 is the first hidden layer. We go, and the last one is that the mutual information between the y and y hat. And the best thing happens when all of these things are the same. It means they are equality, not inequality, and so we are our best possible network. And oops, sorry, it happens. Okay, and another thing is that the entropy, the entropy of x. It means the mutual information between x and x is more than the mutual information between x and h1, and blah blah so on. Okay. Okay, another principle, one principle in the information theory is information bottleneck principle. It says that the network wants to minimize this. It means that we want to minimize the information. If I'm not mistaken, I think it is minimization. Let me see. Okay, I think it's minimization. We want to minimize the mutual information between x and x hat. X hat is the representation of one of the hidden layers, and we want to maximize the mutual information between the x hat and y. So we want to forget x and we want to learn y. Okay, and it is a okay, we have an estimation of mutual information based on some sample size n, and we can have another inequality like this. N is the sample size. Okay, and based on the previous slide, you can see that we have a finite sample bound here, and we have another bound with its limitations. It means that we can't go above more than this. We can't go in this area. Yes, and you can see that effect of depths here, it means that for example, if you have one hidden layer, it seems like this. Two hidden layers, it seems like this. Three hidden layers, it seems like this. You can see there are different lines here. For example, in the sixth hidden layer, it looks like this. As you can see, the most things happen very fast, and the final epochs, for example, red, orange, and yellow that you can see, are very narrow. Yes, and you can see the effect of training sample size. These parts are for the purple, and the best one is for example 84% of training data. Okay, an estimation of mutual information says that if we want to discretize each image X, as you can see like this, and discretize each representation H, the multidimensional discrete probability distribution is like this, that we have P of X H as M of D times M of D, 2, 0, and 1. And P of Y and H comes of D, M of D, 2, 0, and 1. And we can have an estimate mutual information. As you can see here, I had a estimate of mutual information would become between X and H, the summation over X and H, P of the joint probability of X and H times log of P of XH minus log of P of X minus log of P of H. And the same is for Y. Okay, it's just an example of how you can see the mutual information in a PyTorch code. It's nothing to talk about. It's just the summation that we saw before in the form of PyTorch code. Okay, thank you for watching this video and following me.